In this video, we will continue our discussion on how to find the root of a given one-dimensional real-valued function by introducing a very powerful technique called the Newton method. As you can probably imagine, if a method is named after Newton himself, then it is probably a very good method. It is. Actually, we will see that under some mild assumptions, the Newton method will converge very fast, in the sense that we can expect the rate of convergence to be quadratic. Here, let us postpone the technical discussion on the convergence analysis. Rather, we will simply discuss what is this iteration scheme precisely, and we will try to convince the audience why it makes sense intuitively. There are many different perspectives from which we can develop the Newton method. We will take an approach which addresses the geometric interpretation for this method. In the following, we will use the terms Newton's method, Newton's algorithm, Newton's iteration, and so on interchangeably. The audience should be clear that we are referring to the same thing by each of the aforementioned terms. Now, what is a Newton's method? Let us assume that we're given a very good function on one hand and a very good initial point to start our iteration on the other hand. In Newton's iteration, xn plus 1 is defined by xn minus fxn over f prime xn. As mentioned before, we will give a more detailed and rigorous description on what do we mean by saying a function is good and an initial point is good in the next section. Here, let's first try to understand this iteration. Where does this formula actually come from? Well, to understand the meaning of the iteration, let us start from the simplest case where the function is linear. In that case, the function graph is merely a straight line. The desired root x star is located at the intersection of this straight line and the x-axis. Now assume that we're standing at xn. How can we approach x star efficiently? While techniques like the bisection method surely work, it relies only on the signs of the function values at some specific points. Yet it has ignored for the most part what is the shape of the function graph. Actually, as you can see, a very straightforward way of getting the desired root is the following. We can lift xn to its graph xn, fxn on this straight line. And from there, simply follow the straight line like a kid going down a slide. And the function graph will lead us to the desired root directly. In other words, the function graph is sending some indications what should be the most reasonable guess for the location of the root. This is indeed amazing. However, in general, we are not that lucky, as we have to deal with nonlinear functions instead of linear ones. Now, the graph of a nonlinear function is in general much more complicated than a straight line. But don't forget, if it is differentiable at a given point xn, then although we have a nonlinear function, we still have its linear approximation at xn, provided by the tangent line going through the point xn, fxn. Why don't we consider that as a hint of the function, and proceed similarly as in the linear case, by following this tangent line, look at its intersection with the x-axis, and use that point to update our sequence. To this end, let us recall that the tangent line passing through xn, fxn is given by y minus fxn is equal to f prime xn times x minus xn. If we call the point xn plus 1 and 0 its intersection with the x-axis, then we can plug in these two coordinates into the equation, and from there, we can solve xn plus 1 in terms of xn. This is precisely the updating formula in the Newton iteration. In other words, even in the nonlinear case, we can still consider the function graph as our good friend who keeps sending hints leading us to the desired roots. But this time, unlike in the linear case where all the hints are given at a single shot, in the nonlinear case, these hints are delivered sequentially. Each hint is represented in the linear approximation of the function locally, and we have to use these hints one by one to upgrade our sequence of iteration, which will eventually lead us to the desired root. To see how it works precisely, let us consider an example. Suppose that we want to find the value of square root 2, which is the root of the function fx is equal to x squared minus 2. And how can we find the root of this function by using the Newton iteration? Well, let us assume that we start from x0 being 5. Under the Newton iteration, once we achieved xn plus 1 is computed as xn minus fxn over f prime xn, which is equal to xn minus xn squared minus 2 over twice xn. And this can be further simplified into the form xn over 2 plus 1 over xn. Here, the animation shows that how each term in this iteration is constructed by consecutively following the intersection of the tangent line with the x-axis. As you can see, only after a few iterations, we are already pretty close to the desired root. Now to analyze the rate of convergence quantitatively, we have listed below the first few instances of the iteration, as well as their corresponding absolute errors. If we look at the scales of these errors, by looking at the exponent, we see that the exponents are changing from -1 to -2 to -4, -8, until -16. This is a strong hint, suggesting a quadratic convergence. Actually, we can also visualize the ratio of en plus 1 over en squared as a function of n. Clearly, as n increases, this ratio is somehow stabilized around a certain level, which is roughly speaking 1 over twice square root 2, which further justified numerically our observation that the convergence is quadratic. Alright, hopefully this simple example has given you some rough ideas on the mechanics and efficiency of the Newton algorithm. In the next section, we will perform some rigorous analysis to explain how it works and why it works.